Okay, let's have a look at a model which has inhibitor in a deep binding pocket, and the task here is to create a view of the binding pocket which allows us to see just the part of the surface which binds. And the way it's done, it's with an indirect use of a tool called measure contact area. As a side product of this measurement, it also creates a surface visualization of the area which is in contact. And if you look at the first non-comment lines, there is a command of splitting atoms of an FPS residue. And let's have a look at the Chimera page where I discovered this. It's giving a little bit of background there. Going to Chimera main page and image gallery. Here is the one. So let's see how a visualization like this can be achieved. This is a bacterial squalene synthetase. It's a lipid, a long chain lipid, and it can be inhibited with a farnesyl derivative which has a thiopyrophosphate which is not hydrolyzable by the enzyme, so it's blocking it, and also it's something that can reduce the virulence of staphylococcal infections. And so let's see how the script works. The PDB model is 2ZZP, and I'm going to Chimera and I'm open it from here. This is a structure with two identical chains, so we can just go ahead and delete the B chain, colon period B, referring to everything in B, gone. And now the farnesyl pyrophosphate is a residue called FPS. You can see the long chain here. If I select it, so the green lines will show how long it is. And in fact, there are two copies of this FPS in the binding pocket. And they are nicely coordinated with magnesium atoms in the same way as ATP coordinates magnesium in the phosphate groups. Okay, so the first thing that happens is splitting the FPS into a group of its own. The split command has several modes. The most common one is splitting chains, which is default. So if you say just split and the model number or without a model number, so it will just create submodels of each chain. If you have multiple chains, if there is just a single chain, it doesn't do anything. But if you want some part of the model to be a separate submodel of its own, so you can use the atoms parameter there, and let's have a look at the manual page of split. So you can choose any of these things in parentheses, or if you just leave it blank, it will start splitting all the models you have. But the atoms requires an atom spec statement, and you can do the split on multiple atom groups at once. But anyway, now what we want now is to get these FPS groups into an object of its own. As you can see in the model panel, right now we only have the original model as downloaded from PDB with the bead chain deleted. So I'm running this one command at a time so you can see exactly what happens. So now the FPSs have been moved into a submodel of their own. So there's FPS 658 and FPS 657. Both of them are in 0.1, whereas the rest of the protein is 0.2. And the model panel reflects that. And if you want to make sure what is what, so you can just change the visibility by clicking the show button, and yes, indeed, the FPSs are now in a different model. Now, a side effect of this was that we lost the dotted lines which show the metal coordination of the phosphate to the magnesium. Because they are in separate models, you don't consider the coordination bonds between them. And 0.2 indeed is all the rest of this protein, or let's say the protein and the magnesiums. And now the measure contact area, we can have a look at the command measure. So we can do a lot of things. The measurements we have been looking at, like distances and angles, are there as well. So we can just give a command measure distance and give the arguments as the two atom names we want distance for. But for the contact area, the main function is that reports the area of one surface within a cutoff distance of another. And now if we go to this, it needs the parameters of two surface models, which means that we have to create the surfaces for the FPS and protein parts first. And let's see. So first we do the surfaces so that we can do the contact area measurements. And now I'm just going to color the surface in yellow for submodel 0.2, which is 0.1, which is the FPSs. So you can see slightly better that it's indeed pretty tightly in the pocket. And what we are doing here is the contact area between the surfaces for 0.2 and 0.1. If we look at model panel, you'll see the surfaces as new objects there. So MS main surface for 0.1 and 0.2. And clicking on the visibility, you can indeed see that it's only the surface which is changing the visibility. Okay, the next parameter is the cutoff in angstroms. So we are creating surfaces with a cutoff of 3 angstroms. And the first one is done with the color tan, but let's keep it yellow as it is, or maybe lime. Okay, now the lime colored patches are now part of the contact area object, and that this will be seen as a patch object, contact patch, as model number 1. And in reply log, we should see the results of the measurement. But we are not interested in the numbers as such. We just wanted to have the surface created here, and it's actually coming from different component areas, so it has some disconnected pieces. And also some of the connected pieces are calculated separately, but anyway, we have the object there. And now the trick in creating the final kind of two-layered surface for the pocket is to create 2 surfaces with slightly different radiuses. So the other parameters here are for the slab thickness. Let me show you. So if we give just a single number, it will be the width of the slab, but with 2 distance parameters, d1 and d2, we get the starting and ending thicknesses of our starting and ending positions relative to the original surface, which has like 0 thickness. So now here we have d1 as minus 0.1. It took me a while to figure out the American notation that this is actually a negative decimal number, and then it's 0 on the other side. And then for the other contact area, it is in a slightly different position, 2.99, and again, with these numbers, the ending and starting positions are coming. Are they coming in the same positions? There might be a difference of 0.02 here. But anyway, this gives us a thickness of the slab of 0.1 angstroms. And let's do the other one, which goes into a slightly different position. And now we don't see much of it because it's behind this lime green object there. But in the model panel, we should see patch 2. And yes, it's here. And now for cleaning up the visibility, we can go to hiding the surfaces of object 0. And now we do have the lime surface and the cornflower blue surface, both of which are representing the surface contact area measurement for the contacts between the FPS ligands and the protein. Okay. Now, show is similar to display, but the difference is that the show only shows the atoms and bonds for whatever is given here, and it's hiding the atoms and bond for everything else. This is neat if you want to hide anything that has been displayed for whatever purposes here, like this arginine and tyrosine, which make contacts on the sides of the ligands. We are not interested. We only want the FPS and the metal atoms. And just to show you how the magic word ions works, so it's built into Chimera, so it knows about certain groups being ions like sodium, zinc, magnesium, cobalt, etc. So there's a dictionary of which groups are ions, and so only those would be selected by the keyword ions. And FPS, that's the farnesyl pyrophosphate, and if we take FPS or ions, so now we have both of them selected. And going for show, so we should be hiding the other side chains that were displayed before. They are gone. And then we want to get rid of the ribbon, so tilde for undoing the ribbon command. And there we go. And now the problem is that the surface area measurement also created some small bits and pieces that were within this 3 angstrom cutoff. And we would want to get rid of them. And this is the new thing I learned from this. There is a toolkit called SOP, which is short for Surface Operations, and that is used in line 20 here. Let's do some coloring first. Oops. What do you think will happen when we do this command? It looks kind of cryptic. Something will be colored white, but what are the parameters A and C there? We might look at the command index for finding color. And now all of these things which are given with a comma after a color name are normally different objects that are colored, and A is atoms. So in this way you can give separate colors for atoms or ribbons or surfaces. I used it in a previous instance to color just the surface of our FPS before the measure distances measure surface area was done. But then what is the C? Well, it is the atom spec here, and let's go see what is C. So if we just select C, so it would seem to be all the carbon atoms. So mousing over, you can see that we have C1, C11, C6, C10, etc. And so when you do the color white of the atoms for the carbon atoms, so now they are colored white. And for prettiness, there's also set silhouette, which is the same thing as going to the effects menu and choosing the silhouettes to be displayed. It seems they already were in our preset. Now this is the thing without silhouettes and setting silhouettes. Yep. Now they are at least with nice thick lines. And now the SOP thing. So let's have a look at what we can learn of surface operations. And one of these things is called hide dust, and it is meant for just cleaning up those small debris that are dropped on the floor or left floating next to our real nice big surface. So this here and this here are kind of loose objects we'd like to get rid of. And this is something that requires a parameter, which could be size or area, and then when you give it a number as a parameter, it will take out pieces smaller than that, and I'm happy to have somebody done the work to figure out the parameters. So we are doing this hiding of dust for objects 1 and 2, which are the patches created by the measure surface area tool. And if you observe the loose pieces here, as expected, they disappeared, and it seems that there was a tiny bit even here on the side. So this is nice and fairly clean now. And then the last bit of cosmetics is creating the dotted lines to connect the phosphates to the magnesium atoms. So for that, we need an extra copy of the same protein, and then we are just leaving the FPS to be there, and in that way create the dotted lines for an FPS, which is exactly in the same place as this one, because we haven't been moving it. Rotations don't count because the whole universe is moving. We are just rotating the whole coordinate system. So a new copy of this squalene synthetase, getting rid of the B subunit, getting rid of the ribbon, and then just showing the FPS and mg in model 3. And now you can see that we have the dotted lines there again. And as the final thing is putting the newly created or newly loaded FPS into a wire model. So we can check with model panel how it looks. So 0.1 has our original FPS. It's there, and now underneath it we have just the wire representation and the dotted lines. And if we hide number 3, so you can see the dotted lines disappearing. We also have the magnesiums doubled so that we have magnesiums of model 0, actually 0.2, and model 3 just on top of each other. So we needed a full copy of another protein. We might have deleted everything but the FPS, but it's enough that they are just hidden, and we have now the finished product with a nice binding surface that is with a different color in the inside and in the outside, and also with a thickness of 0.1 angstroms. Sometimes when you have two objects which are exactly in the same place, for instance, you superimpose two copies of the same molecule. So when they are in different colors, the calculation of the ribbon positions has a little bit of an uncertainty, and the rendering then will create kind of random looking pieces of one color somewhere and the other color somewhere, which is seemingly on top of each other, even if they should be in the same place. And we would get a similar patchwork of colors if we created these surfaces in the same place, but because they are with a distance of 0.1 angstroms, so we have clean solid color for both the outside and inside. I wonder if this design would be feasible as a flower pot, obviously in a much magnified size, not in the nanoscale it is not. Now we would just need a small bottom plate to place it on a table in a balanced way, and then this would be good enough for holding a bunch of tulips or FPS molecules if you wish. But this was, even if this was complicated, it's kind of straightforward once you start analyzing it line by line, so you can pretty easily see all the things that were done here. The last bit here was a focus command, which would just center this on the screen and place the center of rotation right there. But this is the surface tool, and